Okay, so we got two sets. So what we'll do is one of you do the ones that starts with A, and one does the ones that start with B, and we'll just share the load. So who wants to do A? Okay. Oh, even better. Yeah, that's fine. That's exactly what I wanted you to do. Yep. Oh, sorry. Yes, so do they commute or do they not? Do you end up with the same answer? Yeah, you end up with 10 times the first derivative of f of x. So in this case, doesn't matter what order you do them in, the two operators are said to commute. Okay. Now, I broke them up like this to sort of show you stepwise. When you're actually doing it, you don't necessarily need to show every single one of those steps. It was just an attempt for clarity. Normally, you just go here, maybe to here to there, or just from the beginning to the end, right? On a test or something, you don't have to show, you know, how you're breaking it up. It's fine if you want to do it that way, you just don't have to. Okay, any questions on commuting? It's just simply do that. If you get a same answer for either order, then it commutes. If you get a different answer, it does not. It's a binary yes or no. Linear operators. This is the part for the last question on the current homework. Okay, so linear operators are ones that follow these two sort of sets of rules. Oh, here's my notes. Okay, so a linear operator is one that you can break if you're taking an operator and applying it to the sum of two functions. It's equal to the operator applied to each function first and then adding. And the other caveat is if it's the operator is adding or is being applied to a function times a constant. If it's a linear operator, then you can pull the constant out and have the constant times the operator times the function by itself. Right? If those two conditions are met, then the operator is a linear operator. Linear operators are really convenient to use because if we can find a way of pulling two things apart, we can apply the operator to them independently and then bring them back together. Right? There's some functions where that's going to be really handy to do, and so it's handy to use linear operators. Most of the things we're going to be working with are going to be linear operators. So being able to check, like is on your homework, is this a linear operator? Does it follow this behavior or not? You know, is going to be important to be able to check. Questions on that? Just a mathematical definition of what we mean when we say a linear operator. When it's applying to a function, this is the big one. If you can break it up into two summations, or to the summation of two functions, a linear operator is one where you get the same result. If you break those two functions up, applying the operator to each one independently, then you add them back together. Any questions? No? Okay. Okay. Eigenvalues. Oh, graph notation is the next one. Okay. So when I initially took quantum mechanics, this is the thing that caused me the most confusion because I thought it was a chemistry term. It is not. This is a math term. Right? So eigen is when we're talking about eigenfunctions, eigenequations, eigenvalues, all that eigen type stuff, it's a math principle as opposed to a chemistry principle. Eigen is German for proper or characteristic. So an eigenfunction is the characteristic function for this particular thing. Right? An eigenvalue is the characteristic value for this particular thing. Okay? And again, this is math, not necessarily chemistry, although it gets applied to chemistry a lot, or at least quantum stuff. So an eigenvalue equation is one that has the general form of operator times function gives you back a constant value times the same function. So this function and that function, those two are the same function. So you apply an operator to a function, you get back the function times a constant. It's a very small subset of equations that will work out. Right? So you have to have the operator paired with a constant and applied to a very specific function for all these moving parts to work out at one time. So let's say we have a function. The function that's within this eigenvalue equation right here, this function is called an eigenfunction. So in order for an eigenvalue equation to work out, you have to have a function. If it's working out, that function gets labeled with the term eigenfunction. So the eigenfunction would apply up here, and there. So we're going to use this omega hat to mean just some general eigenfunction, some function that fits this particular pattern. The constant factor is going to be called an eigenvalue, and we're going to use lowercase omega. So omega hat applied to our wave function is equal to our eigenvalue times the eigenfunction. So in words, an operator applied to an eigenfunction is equal to an eigenvalue times an eigenfunction. Or if we want to get rid of the German-esque eigen, an operator applied to a characteristic function is equal to a characteristic value times that same characteristic function. This particular thing is super limited in the number of equations and operators that works for, right? You can imagine that there's only a certain number of functions that when you do some sort of mathematical process to it, you get the constant and then that same function back. Not a whole lot of stuff, right? So eigenvalues, eigenfunctions, and operators work together. You can't just have any operator apply to, you can't have a general operator apply to any eigenfunction and get back an eigenvalue. These are paired. So you get the operator applying to a particular eigenfunction, giving you a particular eigenvalue and a particular eigenfunction. They're all paired up. Right? So just because something is an eigenfunction for one operator does not mean that it's going to be an eigenfunction for another operator. The operator and the eigenfunction are paired. They have to work together. Make sense? Or
Makes sense.
is the definition somewhat workable? Yeah? Okay. complicate things, yay, is what's called Dirac notation. So if you remember, we were talking about the probability distribution function as being so our probability of x was equal to the integral from negative infinity to infinity. I guess we technically should have the normalization in there. Psi star times psi d tau, right? That's what we were calling our probability distribution function for, by Born. The thing though is, writing this out can get a bit tiresome. Yeah, they are super lazy. And they just add complications to it. So in 1939, Paul Dirac created something called the Bra-Ket notation. It's also called the Dirac notation because, name stuff after dead people. It's a notation that's used a lot in linear algebra, but we can also use it for our diff-EQ, our differential equations, and for a lot of this. So the way that it works, there's two ways that you can use it. So let's say we have two functions. The first term, the first part is called the Bra, and the second part is called the Ket. So you got your dividing line, that is the Bra, that is the Ket. Okay? So the Bra-Ket gives you the integral. We can keep writing negative infinity to infinity of the first one is the one that is the complex conjugate. So it's the complex conjugate of that function times our other function, d tau. Right, so instead of writing out all this other stuff, well, I guess technically you'd have your normalization constant squared. Most of the time, we're just going to assume that all these functions are normalized because they have to be, right? So, Bra-Ket. That's a T, not an L. Okay, so if you see something written like this, what it actually means is all that. It's just a shorthand notation for saying this. We're going to be using this so much that we have a separate notation for it to just simplify our lives from having to write it over and over and over again. The other form is when we have an operator thrown in. Okay, I got the same thing. Okay, so this is still a Bra, that's still a Ket, but now you're applying it to an operator. So this would be your normalization, negative infinity to infinity. So you have your operator applying to the Ket component and then being multiplied by the Bra component. This gives you typically the average value for your operator. And this is why these notations of the greater than or less than become a bit confusing. We unfortunately double dip in a lot of stuff. Right? So this is the average value for that operator. Just like we were talking about, remember that this is your probability distribution function. And so if we're multiplying that by some sort of a functional operator, you get back the average or the expectation value for that operator. Right? It works the same way as when we were talking about those the probability distribution functions a bunch of slides ago. Same sort of idea. So this is also Dirac notation. But this one is, so you take the complex conjugate of that, regular of that being operated on by a hat. Okay, so Brockett notation gets used in two different ways. If there's two components, then it's the complex conjugate of the first times the second integrated over all space. If it's the second one where you have an operator in the middle, then it's complex conjugate of that times these two paired together. Right? The operator operating on the ket. Okay? There. Well, okay, we got a couple more terms, but not a whole heck of a lot. Questions on Dirac notation? It ends up being just, this is defined as, that's what that notation means.
So the complex conjugate, which is like the O and the line in the middle,
Mm-hmm.
that's the same as it's basically a function and its conjugate, right? If it was a complex function.
Yeah, so this would be,
So that's the same as psi conjugate, right?
no, this is, to be the psi conjugate, this would have to be psi.
Yeah, so it's
The star means the conjugate of what it's next to. So if these are two different functions, right, it would be the complex conjugate of this function. So you take whatever this function is and the imaginary component, you flip the sign on that part, and then you slot it back in as that. Okay? This is the one that gets a bit confusing. Let's see how we're doing. I think we'll do this and then maybe take a quick break. Because, yeah. Okay. You'll work with them enough that you'll get it. It's probably a good idea now to start committing it to memory, I'll say. So essentially the answer is yes, it's probably a good idea for you to memorize them. Okay, when we're saying something is a Hermitian operator, that is one that follows a very specific relationship. So it's an operator that satisfies this relationship, right? So you have two functions. The operator operating on one function times the complex conjugate of another is equal to flip the functions, right? So this one was operator on G, this one's operator on F. So you flip the functions, take the result of this whole thing, and then take the complex conjugate of it. So if they are equal, then it is said to be a Hermitian operator. Okay, if we write it in, this is kind of where Dirac notation gets used to sort of simplify, to identify what we're really talking about. So in Dirac notation, this would be f of x omega hat g of x. If this is equal, to that. This one's the conjugate of the function in the bra part. So the bra, the first part of the Brockett notation or the Dirac notation is the complex conjugate. And then the second one, this is what the operator is being applied to. So to me, this is a little bit easier. The Dirac notation is a little bit easier to highlight what's being flipped and what's really going on, to really highlight that the F and the G are swapping places. Now, one of the things we can do, going a little bit back to our concept of complex conjugate. If something is real, so if a value is real, like z, then z would be equal to the complex conjugate, right? If z is equal to 3, right? Then the complex conjugate of it would be z, so this is the real component, is equal to 3 plus the negative or the flipping the sign on the imaginary component. This didn't have any imaginary component, and so the complex conjugate would have the negative of the imaginary component that it wasn't there, right? So, oops, sorry. Right. So if you're flipping the sign on an imaginary component and there is no imaginary component, then it was real to begin with. Right? So this is one of the checks to see if something's real, is you take the complex conjugate of it. If you get the exact same value, it's the entire, the original thing was a real value to start with. Okay, so let us do a test to see if something is Hermitian. Okay. I'm going to use a little bit of the board space. Okay, so are you guys okay with this being, with your Dirac notation being our shorthand for what was up there for the definition of Hermitian? Okay, so let us test if our good old d by dx operator is Hermitian. So we're going to take the integral over all space of f of x star d dx g of x dx. And we're going to see if this is equal to the integral of g star d dx. No, sorry. G of x d dx f of x dx. And then have this whole thing here. Take the complex conjugate out. Right, that was our starting point. We're now just trying it with a particular operator. Okay. So what we're going to need to do in order to take this integral is we're going to have to use integration by parts. Right? So if you forgot integration by parts, if we have two things multiplied together, we can do this as the integral of u of x d over dx v of x dx would be equal to u v, or our function uv, minus integral v of x d dx u of x dx. And the reason we do this is sometimes it's easier to take the derivative of maybe the u function or the v function And so the reason that you would do this integration by parts is sometimes doing the derivative of one of these is easier than doing the other one. And so that's one of your mathematics operations. Okay, so essentially if you compare this with the one above, f of x is our u of x, and g, g of x is our v of x.
Wait, so what's ddx? So what's ddx?
ddx is our operator.
So we don't really use that in the integration by parts, it just stays alone.
This here, that is integration by parts. This is what you'll generally see if you're looking on the web. They use u and v commonly when it's listed out for integration by parts. Right? So this is what you'll find if you Google integration by parts. It'll look like that. Okay? But we're using f and g, and so in this function, or in this line above, where we have u, that's f of x. Where we have g, that's v of x. Or where we have v, that's g. So we can put our proper terms that we were using before back into this equation and see what it looks like. Okay. Oh, sorry, it's f star. Right, because up here it was f star. Okay. Integral, but negative infinity to infinity, f star x, so the complex conjugate of f g dx, g of x, dx would be equal f star of x, g of x minus integral negative infinity to infinity. These two evaluated. Let me give myself a little bit more room. Okay. Now, so we're going to take f of x, or sorry, f of infinity times g of infinity minus f of negative infinity times g of negative infinity. But if you remember, for these functions, there are limits on them, right? Going back to what the probability distribution function is, these functions have to have a limit. So for both of these functions, the limit of g of x as x goes to either plus or minus infinity, it has to equal 0, right? That's one of the definitions of our functions. And then the limit of f of x is the same thing.
Is that same as f conjugate x?
Yep.
So they look zero.
Okay, so this essentially, this first part here, that's 0, right? So that gives us that is equal to 0 minus equal to that. Okay, so, let's see. We are going to see, so this line here was we were taking this part, using our integration by parts to come up with our end answer, right? To put it in a different form. This part here, which was our first part, is equal to that. So we're now going to evaluate is our result there equal to that, right? Which was the definition of Hermitian. So we're going to see is, we're going to replace this part here with what it is equal to over here. So that's the negative of the integral from negative infinity to infinity of g of x d dx f of x star is that equal to the negative of integral negative infinity to infinity g star x d dx f of x dx complex conjugate.
And why is it negative?
Because we have a negative here. Right, so this here would be that.
I was just negative both sides.
Yeah. Or, well, sorry. This part here, if we're doing the Hermitian thing to it, would be flipping these two around and then taking the complex, sorry. Okay. This here is equal to taking the complex conjugate of what's within here. So if you take the complex conjugate, it's of the entire thing, it's the same as taking the complex conjugate of this and then the complex conjugate of that. Right, so this part here is equal to that. The negative here is because you got a negative. Well, the negative here is because you got a negative there.
Okay, so like on the top, on the second line, right? You said left side should equal to right side.
Yes.
Left side equals to negative thing. So the negative thing should equal the right side on the second line, no?
I got one more thing to add, and that might make sense. Okay. Is this equal to what we got up there? Okay. So, are these two equal? The answer is no, right? You got a negative sign here, no negative sign here, but otherwise they're the same thing. Right, so they are not equal. This is that, right? I just move that down. And then this, if you use your the integration by parts, this can be replaced by that. And then we do apply the Hermitian thing to this one, giving us that. And you can see that the two are not equal to each other.
Okay, so what do you do with the left side function to get the middle thing? So I know that, you know, the left side function we got it from integrating apart the left side of the second line,
Right.
which is not equal to the right side of the second line, which makes sense.
I think I see. This is the complex conjugate with that.
Ah, that's right, cause it's this, okay.
And we swapped where the stars were. Right, so this became no star, and this one became star. Between here and there.
Okay, that makes sense.
Okay, and the reason that I put this inside of parentheses, the negative here, is not affected by the complex conjugate, so I can pull it out. And the reason I did that is so that this looks the same as that, and you can clearly see that the negative sign versus the non-negative sign.
So whatever you get,
So what we're saying here is that the derivative, this is not a Hermitian operator. A lot of the functions, all the wave functions, or all the eigenfunctions that we're going to be using that have well-defined answers are Hermitian operators. And so this is another check that we're going to have to use on the operators that we apply to our wave functions. So we can fix this, right? So this is not Hermitian. Am I spelling that right? I did not spell that right. Hermitian. Okay? That is not Hermitian, but let's make a slight modification to it and see if we can come up with something that is Hermitian. And the reason I'm making a slight modification is to make it Hermitian. So let's do the same thing, except we're going to modify it so it's equal to I h bar. Yeah. So sorry, negative I h hat. So we're taking what we had before, multiplying it by I h hat d dx. The only thing we're going to do to it is we're going to multiply it essentially by a constant and see, does magic happen? So, essentially as we go through, we're just going to put an I h hat in front of wherever you see d dx. Right? So, integral f star x negative I hat h hat d dx g of x dx equals g star of x negative I h hat d dx f of x dx. Separate. Okay, again using integration by parts, we will get, so it's essentially the same thing except instead of the d dx we have the negative h hat. So skipping down to the equivalent of this line, we get integral negative infinity to infinity of f x star negative I h hat, or sorry, h bar, I don't know why I was saying h hat, h bar e dx d of x dx is equal to, again, f star of x g of x negative infinity to infinity. This still is equal to 0. Minus integral infinity g of x minus I h bar d dx f star of x dx. Okay, so same thing as before. We got the limits for g of x goes to 0 as x goes to infinity or plus or minus infinity. Same thing here. So this, that's equal to 0, just like before. Okay. So this is, negative infinity g of x negative I h bar d dx f of x dx. Should have had a dx here, doesn't really do anything, but technically should have had it. Okay, so this would be equal to the negative, like we had before, negative infinity to infinity of g. So we're going to take the do the complex conjugate of everything. We're going to be applying the complex conjugate. We now have an imaginary component in our operator, and so we take the complex conjugate of this, right? So negative I complex conjugate is plus I. Right? That's sort of the definition of complex conjugate. That's what we're doing. And so what's inside this set of parentheses is plus I h bar d by dx f of x right. You can think of the complex conjugate as a switch, right? If you take you complex conjugate everything, put it in a set of parentheses and say you're going to do it again, you get back your original function. Right, so you can switch between the two. So if, let's see, this applying our integration by parts gives us this. Applying, taking the complex or uncomplex conjugating it, or taking the complex conjugate, right? So this is equal to that. We apply the complex conjugate to what's inside the parentheses, we get back this function. You good? Okay. And then we check to see if this is equal to what we had before. So is that equal to the integral from negative infinity to infinity of g star x of negative I h bar d dx f of x dx, right? This negative sign, you could bring it inside, put it right next to that I. They are the same thing, right? Or you could take this negative sign and pull it out, and you end up with the same equation either way. So by putting the I in there, we switch something from being a non-Hermitian operator to being a Hermitian operator. Hermitian that is one of the reasons why we're using the complex numbers.
Alright, so the middle functionality, right? In that you have plus I h bar,
Mhm.
and then you're gonna take conjugate of that.
Yes.
So shouldn't that make it negative? Because if you make, like, if you take conjugate of positive I, you get a negative I. Then negative goes outside, becomes positive, so you still have a positive I inside, and the whole function is positive then.
Yeah, no, if I take the complex conjugate of this,
Uh-huh.
then I get the negative sign,
And then you bring it outside to multiply by the negative.
which is this. Right? So the complex conjugate of what's within the side of the parentheses is this.
Yes.
And the negative sign matches up with that negative sign. Ooh, aha.
Hold on.
See if you can spot it and get the bonus point. I'm not always good at copying things down from one line to the next.
Should be a negative sign.
I dropped the parentheses and the complex conjugate from this one. I didn't copy it right from the very first line.
The last line, the equality is still like messing me up in both cases. Because like in this case, right, you had a function and then you took a conjugate of that, would somehow give you numbers.
So these two are the same, right? So if I take the complex conjugate of what's within the parentheses, I get back that function,
Oh, since you don't have 9, because like
because there's no I here.
so that function is real, so that's taking conjugate of that is still the same thing.
Well, the operator is real. We haven't really specified what these two functions are, so they could have imaginary components. And so the function could, be a complex number that we get out of it. The key part here is that because I have this complex conjugate here, if I take the complex conjugate of everything that's within the parentheses, I get back that function.
So if you take a complex conjugate of a complex function, you get
The complex conjugate of the function.
so it almost sort of like cancels out. So if you have a g conjugate x, right, and you take a conjugate of that, you get back g of x, which we just did right there, right? Or no?
Sorry, one more time?
So if you took like g conjugate of x, and then take a conjugate of that quality, would you get g of x?
Mm-hmm. Because each one of these, the star means that you flip the sign on I. So if you flip the sign once, and then you flip the sign again, you get unflipped. It is vaguely, but not quite, like multiplying stuff by -1.
Alright, so then that makes sense.
But not really, because it's only taking the imaginary component times -1.
See, okay, then the left side function, the left side, that should equal the farther more right side. Because if you were to take conjugate of that, right, that right side,
So
then you
this
get that.
one
Yeah,
should equal that one?
okay, in my mind, if you were to take conjugate of that, right, then g conjugate x will become g of x,
Mhm.
d dx, and then f of x become f conjugate x, which is the
Mhm.
same on the left side.
Yep.
So
Except,
it's not, oh, the negative sign.
the negative is why they're not equal.
Then how did it get lost in the third function? It's in the middle.
In this one?
No. In the last line, right? In the middle, you have a negative sign.
Yes.
And then going to the right side, you lost it.
Yes.
How come?
Let me grab a red marker. And I'll draw where things are coming from.
Yep. Yep.
Okay, and then this is the same, these two are the same. If you apply the complex conjugate of what's within the parentheses, you get this.
Okay, but let's say if you don't do the middle function or middle part, right? If you just solve the left side function and we get integration by part, and we get that, if it's not equal to the right side, then they're not Hermitian, correct?
Yeah,
Okay. If they don't look the same, okay, it's just not.
well, so this part here won't necessarily look the same as that one,
Therefore, they're not.
because this one's wrapped inside a set of parentheses with the complex conjugate on it. This one here isn't wrapped in a set of parentheses.
I think it makes sense. Because the right side, you still have to do a thing to it, which is to take the conjugate of. And if that looks same as left side, they are Hermitian. But because the negative sign does not match up, they're not Hermitian. Okay.
Yes.
I think that makes sense. The left one makes sense, the right one is like, okay. Last line.
The right, the point here is because we have this, we also take the complex conjugate of this, and so we're flipping the sign here, and that's what makes it work out. Because down at the bottom, what was causing us issue was the negative sign here, but not, well, I guess the negative sign here that wasn't over here. But if we have an added I term in there, then by taking the complex conjugate of that, you're introducing that extra negative sign, which makes everything work out.
Well, then on the left side, or on the right side, the last line where you had three equations setting equal to each other,
Yes.
on the left side, on that one, you have a negative sign on the side.
Mm-hmm.
But on the farther right side, you don't. So
Mhm.
they shouldn't be equal to each other.
This one's wrapped in a set of parentheses with a complex conjugate.
Which is just changing the sign of I to a positive one. Oh, which is, if you were to multiply negative, okay,
We got two negatives here, so they cancel each other out.
that makes sense.
And so if you take the complex conjugate of what's inside the parentheses, you would flip,
The I's.
well, you'd move this would be starred, and then this would be unstarred, which it is. And then you'd flip the sign on this I here, which would make it the same as this one.
And then the middle one's the left one, which is G prime X.
Okay, we're gonna take a break here.
I think it's